Swayam Prabha. Digital India. Educated India.
So what is an instruction set architecture? So I have a hardware, there are some instructions which this hardware can understand. Those instructions are called machine instructions. These machine instructions have to meet two ends. This should satisfy the need of the compilers and on the other hand it should also be implementable. Okay. So the machine instructions, rather the instructions that are understandable by the machine, have two ends to meet. One thing is it should satisfy the needs of the compiler, and at the same time it should be implementable on hardware. Okay. Now that means when these machine instructions are given to the hardware understands this. What do you mean by implementable on hardware? It should be understandable to the hardware in some sense. What do you mean by understandable to the hardware? The hardware actually interprets these instructions in some form, right. So implicitly there are two translations that are happening when you write a program. So I have a high level language, there is one level of translation I could call translation 1, which gives you a compiled code. In machine instructions, right. So this is an explicit translation wherein you can see the executable code encoded in the machine language, right, the language of the machine. Now these instructions are pushed one by one into the hardware. So the hardware now interprets each of these instructions for execution. So there is an implicit translation that happens at hardware level. So when we are looking at instructions, there is a translation or what we call as compilation, which is explicit, and then there is another translation which we call it as interpretation, which is implicit, right. So in last course I have distinguished you between what we mean by a compilation and an interpretation. What is compilation? I take a program, compile it end to end, convert it end to end, translate it end to end, and create another executable which is in the form of the target language. This is called compilation, right. But then take a program, take every instruction, execute, then take the next instruction, execute, right. So this is actually called as interpretation. Okay. So the difference between a translation, a compiled program and a interpreted program is that this is one interesting example. If I take the hardware, the first level of translation which takes the higher level language program and converts into a machine language, that is compilation. Now this machine language program is taken is input to the system hardware, which takes instruction by instruction, understands it and executes it. Somehow we should know that this is add, this is multiply. So there is something, some semantics associated with the instruction which is understood by the hardware, and that is basically interpretation, right. So when I look at so when I am trying to develop an instruction set architecture, I should look now at two aspects. One thing is there is a great compiler needs so many things, so I need to have those features which will be supported, but at the same time those features cannot be so fancy that it is not implementable on the hardware. So I have to strike a balance between this, and that balance is what gives rise to a bigger classification of computing systems in general, or based on how biased I am to the hardware versus how biased I am to the compiler, right. So, I can be very compiler as an instruction set architecture, I can be very compiler friendly. At the same time, I can be literally hardware, I can make the hardware mad, okay. I could have so much complexity. On the other hand, I could be very much hardware friendly, while I will be very unfriendly to the compilers. So depending on how close the instruction set architecture or how friendly quote unquote the instruction set architecture is to the compiler versus the hardware, there is a classification of computing systems based on that, and that is what we mean by RISC versus CISC. RISC actually stands for reduced instruction set computers. This CISC actually stands for complex instruction set computers. Okay. So, what do you mean by reduced instruction set computer? You have already done in your third semester course, what you did there is a RISC machine. Okay. So, the small hack hardware that you made, the small processor, toy processor that you made was a RISC machine. In sense, what do you mean by that is that this RISC is more hardware friendly. Hardware friendly in the sense that it has minimum number of instructions. Right? Right, and then all instructions are of same length. So, every instruction is say 4 bytes, right. In this case, if I have minimum number of machine instructions. So, I may not have any fancy machine instructions. So, if I have a fancy compiler requirement, right, then I need to realize that compiler requirement using these so called primitive instructions. So, it makes the compiler's job extremely complex, because I have very primitive instructions, and say I have to support, say suppose in hack the hardware that you generated in your third semester, suppose I want to put say protection, I want to introduce segmentation, it will kill you, right. But if I do not have segmentation, we will see in the afternoon's tomorrow's afternoon class, we can't do even compilation. So, we are trying to do something there, but a lot of things that we keep in mind are going to be complex, right. So, for example, if I say that every instruction should be just 32 bytes, I can't even initialize a register of 32-bit length with an immediate value, because I need 32-bit immediate value. The 32-bit immediate value itself will consume 4 bytes. So, how will I have an instruction that will initialize a register with a 32-byte value? It is going to be extremely complex. So, we have to do lot of roundabout ways by which I can go and initialize a register, a 32-bit register with a value, right. So, these are all very difficult things that come up. So, if I have all instructions are of same length, then even basic initialization of constants into registers, like I go and say a equal to 515 and a is a 32-bit integer, I can't assign 515 to a as an assembly language, because if I want to put 32 bits, immediately 4 bytes are consumed, each instruction can be only 4 bytes, correct. So, there are very different tricks that I need to follow to basically get that value of some 500, 510 or something into that value A. It can become multiple instructions, etc., etc., etc. Okay. So I will talk about the ARM instruction set architecture from the RISC point of view, while you will be writing a small mini kernel in CISC. So, I will not bother to teach about CISC, you will learn it through your assembly language, but about RISC we will talk a little bit more in subsequent classes also. So, in essence RISC is hardware friendly, it has minimum number of machine instructions, it has all instructions are of same length. By this what happens, the second level of translation that I told you, namely that interpretation is easy. The con of this RISC is that it is compiler's hell. Okay. It will create nightmares for the compiler, especially when I want to support fancy things. This becomes extremely complex for you to code, translate. On the other hand, this is a complex instruction set computers where this is completely hardware's hell. This is hardware 7 while this is hardware hell, in the sense that it will have hundreds of instructions. The instruction set manual of Intel is an example of this, Intel AMD, especially the x86, right, is an example of this, while on the other hand here ARM, MIPS, these are all RISC machines. Okay. We will have hundreds of instructions, the manual is around 500, just the instruction set alone is 570 or 580 pages, okay, which will basically describe these instructions. So, this is one thing, and they will not be not of same length. If it is not of same length, so I have a variable I associate it with a register EAX or whatever, and I say I want to initialize with any constant, I can do it. So, the compiler need not actually spend lot of time to even initialize a particular register with a particular constant. Okay, are you able to get this? So, if the instructions are not of same length, then it becomes much more easy, but then what is the interpretation is going to be extremely difficult. But surely this is compiler's heaven. Why is the interpretation going to be difficult? Why is the interpretation going to be difficult?
Because of the variable length instructions.
Why?
Because initially we don't know of how much length the instruction is going to come. So before that we have to find out, like based on the length we have to find out what kind of instruction it is, and then we have to disassemble it.
So I don't know. So when I fetch something from the memory, I fetch it in blocks. So so when I fetch something, say I can have 1 byte instructions in x86, okay, then an instruction can run to several bytes. So I could have several instructions in one fetch, or not even half an instruction in a single fetch, and an instruction can start one part and end somewhere else in some other next fetch, okay, it can span across 2 fetches. So if I am going to have 1 byte instruction to say 20 byte instructions or 10 byte instructions, right, suppose I am going to have this variety of things. Now your decoding itself becomes complex, I have to see the first byte, then the second byte, then the third byte, etc., right. But on the other hand, if I have a fixed length, an instruction basically has what? What are the things inside an instruction? What are the things inside an instruction? What will an instruction carry? What do those bits represent? will represent two things, right? It will represent opcode and operands, right? Add something, add is an opcode, on what should I add, it becomes the operand. So every instruction will have opcode and it will also have operands, right? In a fixed length, normally what happens is we will reserve say 5 bits for opcode, 4 bits for operand 1, 4 bits for operand 2 and so on, okay, let us say like this. So when an instruction comes, I can go and find out what the opcode is, and concurrently I can also go and find out what the operands are, right. If you carefully look at what you have done in hack, that is what you have done, right. In an instruction of 32-bit length, we know exactly how to interpret it. So we know exactly where the operand 1 is, where the operand 2 is, which are the bytes or the bits which are going to specify the operands, that we will know very clearly in a fixed length instruction. So when I get 32-bit, I can fix first 5 bits are for opcode, the remaining things are like this, they are organized. So when the hardware, see hardware is having several transistors, right, one part of the hardware starts interpreting what the instruction is, concurrently the other set of hardware can start fetching the operands, understand and start fetching the operands, right. But in a variable length instruction, I do not know where these type of operands are going to be there. So in a variable length instruction, when I want to decode a variable instruction, I go byte by byte and then find out where the opcode ends, where the operand starts, etc. But in a fixed length instruction, I need not go byte by byte, I have more concurrency in understanding that instruction. What do you mean by fetching the operand, fetching this? I am trying to understand what that instruction is. So my decoding becomes extremely fast, and decoding and the corresponding actions become extremely fast in the case of RISC instructions because of fixed length, while the same decoding and other things become extremely complex in the case of CISC, because I do not know where I should look for the operands. So the decoding essentially becomes almost sequential in the case of CISC. In sequential instance, I have 8 bytes of instruction, I do not know whether 8 byte will finish off, will it have only half the instruction, or it is having more than one instruction, or it is exactly the instruction. So I start looking at byte 1, based on that I start looking at bytes 2, 3, etc. So it can become almost sequential for me to decode an instruction. So that is the basic difficulty. So RISC, so my interpretation at RISC level is going to be extremely easy, while CISC level is going to be complex. But on the other hand, from the compiler's perspective, RISC is very difficult, in sense it takes lot more effort for the compiler to generate a RISC based machine code, while on the CISC it becomes much more easy, right. So this is a classification of computers today. ARM is a RISC processor, RISC-V is a RISC processor, while on the other hand Intel x86 is a CISC processor. So based on how the instruction set architecture is designed, based on the length of the instruction sets, there is now a distinction between two classes of processors, which comes as CISC and RISC. Able to follow? Yes or no? Okay. So let us go to the next step. One thing is, so as I told you, RISC or CISC, the instruction has two parts, one is the opcode, another is the operands. So I could have one operand instruction, I could have multi-operand instructions. Operands are of two types, one a destination operand and a source operand. Suppose I say add EAX, EBX in ASM, EBX and EAX both are source operand and EAX is a destination operand. So I could have an operand that is both source and destination. Now there could be one operand or multi operands. In this case there are two 2 operands here, right. And in addition, okay, the opcode, right, is the decision of what the opcode is, right, should also be made. So that's one very important. So when I am coming out with an instruction set architecture, what should be the opcode? What is the minimum opcode that is necessary? Somebody has to come out with. So what is the list? Why is this list? Right? So this we need to come out with a very clear justification for that. Similarly, on the operand side, there could be multiple types of operands. So this is basically a register operand. Okay, I could have memory operands, I could have immediate operands. Memory operands are those that I want to add a register value with something in the memory. I want to move something from the memory into a register. I want to move something from a register into a memory, right. So every operand can be a register operand, it can be an immediate a value that is. So for example, move EAX comma 100. This 100 is a immediate operand, EAX is a register operand. I can say move EAX comma 500. This is a memory operand. The address of that memory which I am trying to access is the value of EAX, and 500 is an immediate operand. So I could have instructions with one or multiple operands. We already saw last time, right, div some ECX, right, we saw last time, right. This basically gives you EAX, content of EAX by content of EAX by content of ECX, correct. So I could have register operands. Operands can be one or many. So this is a one operand instruction, but actually there are implicit operands inside this. I could have multiple operands, and these operands can be of 3 types. It can be a register operand, it can be a memory operand, it can also be an immediate operand. Okay. So in the assembly language lab class, we will see more of these instructions and operation modes. Okay. So just for our understanding now, we need to understand what are operands. On the other side, how do we fix these operands, size of these operands? So as you have seen in the Intel manual, you would see 8-bit operand, you see 16-bit operand, 32-bit operands, etc. So how do you fix the size of these operands? Opcode will not tell you the size, right? So how do you fix the size of the operands? Database. Data types. So in a programming language, there could be multiple data types. For example, character is 8 bits, so 1 byte. So I will have 1 byte operands. Then we have lot of times where we use short variables, right. So we have that can also be 8 bits or 16 bits. Then I have long variable, I have long variables, I can go up to 64 bits or 128 bits today. So so depending on the size of the operands which your compiler wants, who supports data types? Who is responsible for understanding and and interpreting data types in your? So I have hardware, I have microarchitecture, then I have operating system, then compiler, etc. Who is responsible for interpreting? The compiler is responsible for interpreting what each data type is, right. So if I have a 64-bit compiler, then a normal int in C would be 64 bits there, versus the same int for a 32-bit compiler would be a 4 byte. So I can have inconsistencies in the way I am looking at int declaration int in C, depending on which compiler I am using, right. So to support the needs of the compiler, the the hardware needs to support the different issues that arise during compiling, and one such issue is the length of these operands, and that the hardware has to help. So that is how operand sizes are being fixed, right. So Intel as such supports 8-bit operand, 16-bit operand, 32-bit, 64-bit, now even larger. Are you able to follow what I am trying to say? So this is how I fix operands.
So what about languages that do not explicitly define a type?
Finally the compiler has to interpret it. Your syntax is different, you have a syntax, right. So you go and say that within that scope you can make a scope based type analysis, correct, right. If you, when you are studying your POPL, right, principles of programming language, you will be learning, hopefully you will be learning lot more other things. So the scope, what do you mean by a scope of a variable? Suppose I am assigning say a variable C to an integer, automatically I will go, so it is in the scope of an integer, so I will go and declare C as an integer. This is how many programming languages do interpret what it is, right. Suppose I go and say C equal to A plus B, very interesting here, C equal to A plus B, right. Now if A is floating point and I have not declared B, I can go and say B is also floating point, because this addition, right, there are two adders, one adder which is a integer adder, another adder is a floating point adder, which could have several integer adders internally, but a floating point adder addition is different from a integer addition. So here itself I have to see whether both are, one of them is floating point, then I will make this a plus as floating point. So when I interpret this, I will use just add if A and B are integers, but if one of them is a floating point, then I need fadd. This is Intel instructions. So the compiler actually sees the different variables there, and based on those variables, the types of those variables, it will come out with a conclusion of whether it is a floating point or integer, okay. So lot of context dependent analysis happens in weakly typed languages, where the types are not explicitly stated, nor the language insists that the types need to be stated. There are a lot of programming benefits. There are a lot of benefits for the programmer if the language is weakly typed, right. If it is very strongly typed, it makes your verification easy, but for the programmer it may not give you that much amount of benefits. So what are weakly typed and strongly typed languages, you will learn more in your POPL course, your principles of programming languages course. But as far as we are concerned, there are some data types and that dictate the size of the operands. Now how do you go about opcodes? How do you design that? I need add, I need subtract, I do not need this. So how do you come out? Is there some systematic way? Suppose you are asked to design a computer tomorrow, like we did design hack. How did we arrive at the different opcodes? No way. Who will give you the opcodes? You are designing an ALU depending on the opcodes, correct? Please understand this. The hardware is not still available to you. You are now talking about the interface. You are now talking about the instruction set architecture. After that only you are going to build an hardware, right? So who will decide what are the instructions that should be inside or what is the process that you would like to follow when suppose you are asked to build an architecture of what would be the instructions inside that. So how do we arrive at an instruction set architecture? This is a question. Are you getting what I am trying to say? We basically go through a lot of experimentation on this. This decision of what instructions that should be put inside an opcode comes out of lot of empirical analysis. Empirical means experimental analysis. So you take lot of examples from the domain. So your system is expected to serve in different domains. It might be that I need to open browser, I may have to do some e-transactions, I may have to support some multimedia facilities. So your system, and I have to do lot of scientific computation. So every system will have certain role for which it is designed for, right, and from there you take all the applications in that role and understand what are the common functionalities that are executed by those operations, by those case studies, and those functionalities, the common functionalities, eventually translate into opcodes, right. I will do lot of additions, so add should be one opcode here. I will do lot of bitwise manipulations, so bitwise and bitwise or and bitwise not, they should be part of your instruction set architecture. So like that we go and look at different applications for which the system has to cater to, and then depending upon the need of the application you start introducing instructions which shall match the need for the application. So the instruction set architecture, at least the opcode, what are the opcodes that need to go in, this is completely dictated by the application or the application domain for which the processor is intended for. Suppose I am trying to make a network processor and there I go and put some fancy multimedia instruction, right, it will be useless, right. What sort of instruction will I put in a network processor? I will try and put certain packet processing instructions, because a network processor which is going to be sitting inside a router is going to get packet, it is going to process that packet and send it across or make some decisions, okay, right. So when I am looking at an opcode for a network processor, I will put certain things related to packetization or related to retransmission there, rather than putting some multimedia instructions there. But when I am looking at a home PC or a processor for your iPad or this thing, we will start looking more on the media instructions, right, multimedia instructions, etc. So there is enough amount of work that need to be done, there is a lot more work that need to be done in identifying what are the opcodes, and for each of those opcode what are the types of operands that opcode can support, and so how do you codify those operands. All these things form basis of how do you develop an instruction set architecture, okay. So in tomorrow's afternoon class, tomorrow morning I will continue on this, but tomorrow's afternoon class we will start looking at the CISC architecture of x86, that will be a very good case study for CISC, while for the RISC we will do something with respect to ARM processor, okay, fine, okay, thanks.